Okay, so in this video, we will discuss measures of variation. There will be 4 different measures, the most important one being the sample standard deviation coming from the sample variance. And this will really complement perfectly our measures of central tendency. So the assumption here is the same. Suppose that we have a sample of n values, and we again will order them from the smallest to the largest. So x1, the smallest value, is less than x2, less than x3, up to, say, n. So we have n values. Now, some could be equal. You could have x1 equals x2, that's not a problem. As long as they're in increasing order, everything's okay. Now we sometimes will denote x1 as simply being x min. To say it is the smallest value of our set, and we'll sometimes also write instead of xn being simply x max. Okay, so the first measure of variation is very simple but not that useful, and you'll understand why as soon as we see how it's defined, and that is the range of a data set. The range is quite simply the maximum value of your set minus the minimum value of your set. Let's consider a simple or 2 simple examples, and then we'll ask the question, why is this not so useful? Suppose that the first set was 1, 5, 9, 13. Well, then our range is the largest value, 13, minus the smallest value, which is 1, which gives us a range of 12. Simple as that. If we had 7, 8, 9, 10, let's go with 15, then the range is again the largest value, 15, minus the smallest value of 7, and we have a range of positive 8. That's what the range is. That's all it is. Maximum value minus the minimum value. Now, why is it not a very good measure of variation? Well, think of it. All we do is we take 2 values, and only 2 values of our set. We take the largest one, the smallest one, and find the difference. What if you had a set of, let's say, 2,000 values? By computing the range as your only measure of variation, you are ignoring roughly 2,000 values of your set. This is horrible. So, simple measure of variation, not very useful, because we ignore most of the values in our set. So not very good. Now, and this is what we are looking for, the standard deviation, but we'll first look at the sample variance. Once we have the sample variance of our set, the deviation is very simply computed from the variance. The symbol for this is a lowercase s squared. And how is it computed? Now in this measure of variation, we will not ignore any value of our set. The idea is we want, on average, to know how far are the values from the sample mean x bar. So before you can compute the sample variance, you first have to compute the sample mean of your set, and if you remember, this is simply the sum of all your x values. So add up all the values in your set and divide by the number of values. So now once we have the average value, the sample mean, we want to know on average, are the values of our set close to the sample mean or far to the sample mean? Well, to find the distance, we simply take the value minus the sample mean. This will give us a distance, but we want a positive measure, and so we will simply square this difference. So we first take x1 minus the sample mean, because again we want a positive measure of distance, because x1 minus x bar is the distance between x1 and x bar, but x1 will be less than x bar, and we'll have a negative number. A measure of distance is positive, so we simply square this, which will guarantee that in the worst case, this would be 0, or, in most cases, strictly positive. And we do this for all value in our set. So plus, now x2 minus x bar squared, all the way up to our last value, xn minus x bar squared. But this is now a total sum of distances squared, right? This is the distance squared between the first value of our sample and the sample mean. This is the distance squared between the second value of our sample and the sample mean up to the distance squared between the last value of our sample and the sample mean. We want a weighted measure, so we divide by, and here's where it's a bit subtle. You're thinking, well, we're summing 1, 2, up to n terms, so if we think of an average, well, we divide by n. And here, this is where it's not so obvious, but we do not divide by n, but by n minus 1. Now this may look strange, but there's a very good reason why we divide not by n, but by n minus 1. And we'll understand this later on in the course. For now, just take this as a given. But think of this as this is the average distance squared between the values of your sample and the sample mean, the average value of your sample. We can write this more concisely using our sigma notation, right? If you think of it, well, all we do is we're summing for each value of x. We do the value of x minus the average value, x bar, squared. So we add all those up for x1, for x2, for x3 up to xn. Once you sum all of these distances squared, we divide by n minus 1. And that is the sample variance. Now there is a problem here, right? Suppose the distance between x1 and x bar was 5, then by squaring it you get 25, which is way bigger. So by squaring, very often we are artificially making this measure larger than it actually should be. And this is where now we will construct our sample standard deviation, which will be brought back down to a more reasonable size. And this is very trivial. We use the letter s for the standard deviation of our sample quite simply because s is the square root of the variance of s squared. And that's it. So once you find your variance, take the square root of the variance, and you have the so-called standard deviation, which is a more realistic measure of the average distance between the values of your sample and the average value. Okay, now before we consider an example of our sample variance and deviation, one last measure of, or actually, no, let me do it right now. Let me do an example, and then we'll consider our last measure of variation. Now this is a fair bit of work if you have a large number of values. So let's take a very small number of values. Let's take only 4 values. So 1, 3, 6, and 5. So we have a set of 4 values. Before we can find the variance, we have to find our sample mean. Let's do so. So x bar, we get the sum of our values. So 1 plus 3 plus 6 plus 5 over the number of values 4. 1 plus 3, 4 plus 6, 10 plus 5, 15. 15 divided by 4 gives you 3.75. And now we have our sample mean. X bar is 3.75. And once we have our sample mean, we can compute our sample variance. So let's do so. So S squared. First value, 1, minus the sample mean squared, so minus 3.75 squared, plus, we keep going, second value of our sample, 3, minus, again, the sample mean squared, so 3 minus 3.75 squared, plus, third value, 6, minus, again, the sample mean squared, and finally plus the fourth value, 5, minus the sample mean squared. And of course we have to divide all of this. This way you have to be careful by n minus 1. We have 4 values, and so we divide by 4 minus 1, which is 3. Okay, so now when we compute this, let's find first our numerator. So 1 minus 3.75 squared plus 3 minus 3.75 squared plus 6 minus 3.75 squared plus 5 minus 3.75 squared. And you should find a value of 14.75. And we divide by 4 minus 1, which is 3. Let me double check this quickly. Alright, 4.75, perfect. And if you want, you can divide by 3, and you have approximately 4.9167. Now let's find our sample deviation, which is the root of the variance. So S, the standard deviation, is the square root of the variance. And when you find your deviation, take the square root of the exact value. So 14.75 over 3. And if you calculate this, the square root of 14.75 divided by 3, you have approximately a standard deviation of 2.217. And that's it. This is how you first find your sample mean, which then allows you to find your sample variance, which allows you then to find, quite simply, the sample standard deviation. Okay. Let's consider now, and before I move on, this really is the most important measure of variation. The sample variance with the sample standard deviation. Let's consider now our last measure of variation, which is a comparison between the sample deviation, so the standard deviation, and the sample mean. And this is called the coefficient of variation. We denote this by CV for coefficient of variation. All that is the standard deviation over the absolute value. So these little vertical bars mean the absolute value of the sample mean. Of course, this only makes sense if the sample mean is not equal to 0. So it's a relative measure of how big is the standard deviation relative to the size of the sample mean. You may ask, well, why is this interesting? Think of two simple examples. Suppose that in both cases, you have a standard deviation of, let's say, 10. In the first case, you have an average of, say, 2. In the second case, you have an average, say, of 1 million. Now imagine this being, very simply, data for the profit or loss suffered by some type of exchange. So if you say to me on average you will gain $2, but there is a deviation of $10 possible. So you think, well, this is not so great, right? Because I can make on average $2, but there is a variation, a deviation of roughly $10. So I could easily make $12, but I could easily lose $8 or even more. And so here, this is kind of, in this situation, unpleasant, as the deviation is much bigger than the sample mean. So here your coefficient of variation, 10 over 2, which is 5, which is quite big, right? The sample deviation, the standard deviation, is 5 times bigger than the sample mean. Here we have a completely different perspective. What if you say again you have some type of exchange of any type of good, where on average you will gain $1 million from the exchange, and again on average you'll have a deviation of $10. Then you're saying, well, I don't really care that much, right? Because you can make $1 million, and you can say, well, I can be up by an extra $10 roughly, or I can lose an extra $10. But relative to $1 million, this is insignificant. And this, of course, is, the deviation 10. And this is reflected in the coefficient of variation. 10 over $1 million will give you 0.00001, which is very small. And so you see that the coefficient of variation is important in the sense that you cannot think of the mean as being big or small unless it is relative to the standard deviation and vice versa. So only if you compare both with one another can you really get a feeling for the real situation. Sure, 10 is big, but nowhere near as $1 million. 10 is big and much bigger than 2, and you can see again you are in very different situations depending on the relative size of the standard deviation to the sample mean. And that is the goal of the coefficient of variation. And that's it. Now let's look at, again, two histograms, where in both cases we have the same sample mean, where in one case we have a small standard deviation, in the other case a large standard deviation, to really understand that the standard deviation is an average measure of the distance from the values of your sample to the average value. And this is what it actually measures. So let's imagine that we have two histograms, frequency versus x values. And in both cases we have the same sample mean, so the same average value. Now here's the task. Suppose that we ask here to construct, just by looking at vertical bars being the frequencies for every given interval. And suppose we go for, let's go with 6 intervals. So 1, 2, 3, 4, 5, and 6. Same thing here. 1, 2, 3, 4, 5, and 6. So same average in both cases. Suppose I say to you, construct a histogram here with a small standard deviation. And of course the letter for the standard deviation is simply S. And here we'll ask for a histogram with a large standard deviation. And all you have to remember again is that the standard deviation measures on average how far are the values from the sample mean, from the average value. So with a small standard deviation, it means that on average, the values are really close to the average value. So most values have to be located around the average value. Well, most values therefore higher frequencies. And a high frequency means a high vertical bar. So you have these really high vertical bars around the average value. And as you start moving away from the average value, well, you should have fewer of those because, again, on average, the values should be close to the average value. So you should have very low frequencies as you move further away from the average value. And this would be a histogram where you would have a small standard deviation as most values are found near the average value. Now, of course, having a large deviation means completely the opposite. On average, a lot of values are far from the average value. So you would have a lot of values away from the average value. And as soon as you're near the average value, you'd have very little values. So low frequencies near the average value, high frequencies away from the average value. And that is how you should think of a small deviation. So if you have a small standard deviation on average, most values are near the average value. And so you have high frequency bars near the sample mean. If you have a large standard deviation on average, you have a lot of values away from the sample mean. So you will have bars with high frequencies away from the sample mean. And close to your sample mean, you'll have bars with low frequencies. And that's it. And so with the sample mean and the sample standard deviation, you have two really good measures that will capture the overall shape of your histogram. A measure of central tendency in the sample mean, and a measure of variation in the standard deviation. And that's it.